All right, AP Chemistry folks, this is going to be the second half of um, the Chapter 3 work for Unit 1, and you're going to notice here I found some different software, which means that you get to see my ugly mug while we go through this, so let's hopefully this won't take too long. All right, number 18 here is one that I'm not gonna do right now because it's just like the other problems up above, 17. It's a mole-to-mole conversion, so we're going to skip that one. We're going to go to 19 here, where we have an actual mass-to-mass stoichiometry problem. So actually, we need to read through this first to make sure that you understand what I'm saying and you're following why it's mass-to-mass. All right, so we have potassium cyanide reacts with acids. A deadly poisonous gas, which is the hydrogen cyanide, is given off. And here's the equation for that thing. So that's background information, stuff we don't need in order to solve for the problem. But we can start looking at what we have in terms of the reactants and what in terms we have in terms for the products here. And then we can look at the actual problem. It says if we have a sample of 0.14 grams of potassium cyanide is treated with excess hydrochloric acid. Calculate the amount of hydrogen cyanide gas would be formed in grams. So this tells me it is a mass to mass stoichiometry problem. All right, let's put that over here. We have 0.140 grams of potassium cyanide. 1 mole is, get out the calculator and the periodic table. Potassium is 39.1, carbon is 12, nitrogen is 14. That gets 65.1. Here's our mole conversion step. This is the important step. This is what allows us to compare one thing in a chemical reaction to another thing in a chemical reaction, and it's a 1-to-1 ratio. So you can see nothing there, so that indicates a 1 mole to 1 mole ratio, KCN, and this is HCN. And now I can convert it into a mass. Let's see, hydrogen's 1, carbon is 12, nitrogen is 14, so that's going to be 27. Go through and calculate this thing. And I get 0.058 grams of the hydrogen cyanide gas. So there you go. All right, let's go on to number 20. Fermentation of alcohol. Let's see, this is a fermentation of sugar to produce alcohol through the wine-making process. We have glucose, which is the sugar, converted into ethanol, which is the alcohol, and then we have carbon dioxide as a byproduct. So if we start with 500 grams of the glucose, what is the total possible theoretical amount of the ethanol that we can get? We have a couple of problems here. We start with grams. We're going to grams, but we are also going to liters. So we have two problems here. So let's go to grams first because we can go mass to mass. Notice it's no longer a 1-to-1 ratio. It is a 1-to-2 ratio. All right, so we have our 5. Do this. This is number 20. 500 grams of the glucose, and I'm just going to say glucose instead of writing out that entire chemical formula. And it's probably going to take up about the same amount of space. Let's go ahead and do that. We have the grams of the glucose, and we have the mole of the glucose. Now I need to go and figure out what that molar mass is. It's going to be big. Let's see, we have 6 carbons. We have 12 hydrogens, and we have 6 oxygens. We got 180. Mole ratio step, 1 mole of glucose to 2 moles of the ethanol. So we can go through the next step here, convert it into the ethanol, 1 mole of ethanol, and we have then 46 grams of ethanol. We use ethanol a lot in calculations, and so that's one that I know. All right, let's go through this thing and solve. 500 grams divided by 180 times 2 times 46 gets us 255.6. So there's a 255 grams of our ethanol. Now we need to go to liters of ethanol, because ethanol is going to be an aqueous solution. So, well, in this case, I guess we're looking at the liquid version of it, not aqueous. So we're going to go ahead and use the density to figure that out. So density is equal to grams per liter. So we have 0.789 milliliters grams per 1 milliliter. So this becomes a simple conversion factor that we can use. So we can start out with the 255.6 grams of the ethanol and then use this guy to convert it. So it looks like this: 255.6 grams of ethanol, 0.789 grams is 1 milliliter. Grams goes away. Now I can convert it to liters. 1,000 milliliters is 1 liter. Those goes away. We're left with then divided by 0.789, 323.9. Oops. Let's get rid of all that there and try again. 323.9 liters of our ethanol. So that's how we use density to figure out the volume of a solution after we do stoichiometry. All right, we got to start over, so this is getting wiped. I don't think we have to move down yet because we're on 21 now. And we're looking at gold. We're extracting gold. So we have 29 grams of gold. We're looking for potassium cyanide. So let's go through this problem and read everything. For many years, the recovery of gold, which is the separation, involved the use of potassium cyanide. Not a very positive thing because potassium cyanide is extremely harmful to the environment. But if we're going to use this method, we want to extract an ounce of gold, which is about 29 grams. How much of the potassium cyanide in grams are we going to need? All right, same thing here. We have 29 grams of gold. And gold is 197. That's 1 mole. Now we can go through a mole ratio step. This is going to be a 4:8 ratio. So we have 4 moles of gold, 8 moles of potassium cyanide, 1 mole of it. And then potassium cyanide, I'm going to add that up to make sure, 39.1 plus 12 plus 14 gets us 65.1. It's the same thing as before, I guess. I guess we have used this one. 65.1 grams KCN. Cancels, cancel, 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 cancel. That all cancels. Grams cancels, moles cancel, moles cancel. We're left with our grams of potassium cyanide. Okay, so this is where I'm going to back up real quick and see why it didn't register that I should use this. And that is because the problem asks us to do moles of potassium cyanide. So I need to get this out here, change that to large. Alright, so all that goes away. And we can go back through here and finish it up. That will equal then 29 divided by 187 times the 4 over 8, 0.31 moles KCN. Alright, so there you go. Going on number 2, 22. Limiting reactant. That's the one that runs out first. Good enough. 23. I'm going to start a brand new one for this because this is going to take up some space. There is a couple really good videos about limiting reactant that maybe I'll try to find and post for you. Because I'll show you this one, but since everything is a 1-to-1 ratio, the power of this method isn't really demonstrated. So maybe another problem would be useful. Anyway, let's go through this. This method is called the ICE method, and it works. It's pretty nifty. All right. It's pretty neat. Start off with O3 plus NO gets us oxygen and NO2. And we call it the ICE table method. So we have ICE here along the right hand or left hand side. I stands for initial, C stands for change, E stands for end, and so that's what we're after. So when we're dealing with an ICE table like this, it must be in moles. So let's go ahead and figure that out for our two reactants. Our moles of ozone, that's the O3, 0.740 grams of ozone. It's going to be 48. I guess our answer there. And then we have the nitrous oxide, 0.670 of NO. 1 mole of it is going to be 30 grams. So let's get these guys down. 0.74 divided by 48. 0.0154, 0.67 divided by 30, 0.022. So those are our initial amounts of those two reactants. So we have 0.0154 and 0.022. That's our initial stuff. Now our initial stuff of the products is going to be what we start with at the beginning of any reaction, and that's going to be nothing. The change is related to the coefficient. So on the reactant side, we're going to subtract. On the product side, we're going to add, because over time the reactants are going to decrease and the products are going to increase. and we do so by the coefficient amount. This is by 1 and then a variable, x. 1, x, also there, and then also there. Now, when it's a coefficient of 1 in front of the balanced chemical reactions, we assume it to be there so we don't show it. Same thing here. So I'm going to go back and erase those ones. There you go. And then we can figure out what it is at the end in moles. This is where it gets pretty powerful, and we have to do a couple extra things. So I need to get rid of all this stuff down here so I have some space to room. So erasers back out, get out the large one, and I'm going to get rid of this. Okay, what we end up doing is setting up an equation. We know that the limiting reactant is defined by whichever one runs out. So we say, well, this one would run out if we get to 0. So we say 0 is equal to 0.0154 minus x. We do the same thing for the other one. 0.022 minus x. Oh, we got to put the 0 in there, I guess, first. And then we can solve for x. Now, in this case, it's going to be pretty easy. Each x is going to be that same value because there's no coefficient. So x here is equal to 0.0154. X here is equal to 0.022. And we start looking at this and trying to figure out which one makes more sense. And so let's look at the very first one and say, for example, that nitrogen oxide is going to be the one that runs down to 0. So we're going to say that this is the x we're plugging in. So if we plug in x to the change, 0.022 minus 0.002022 would get us to 0, just like we want. Let me change colors here. That would get us, if we're using this one, that would get us to 0. If we put it over here, though, 0.0 minus, or 154 minus that gets us negative 0.0066. That is not possible, right? We can't have a negative number. So this tells us that nitrogen oxide is going to be the one in excess and ozone is going to be the one that limits. So let's try that again and find out. Let's erase this. Ooh, that's unfortunate. Let's reset this, and then let's use blue. So now we're going to try this one. If x is 0.0154 here, this goes down to 0. If it's x is 0.0154 here, it would be 0.022, 154 gets us, oh yeah, the same thing, 0.0066. This is a positive number. This one works. So ozones are limiting. Nitrous oxide is the excess. Now, what this is, the reason why this is so helpful is that it gives us all the information that we want from the very beginning. We don't have to do a whole lot of extra calculations once we're done. We always work in moles in the ICE table. Over here, 0 plus x is going to be, we're still dealing with x, it's still going to be 0.0154. Over here, same thing, 0.0154. And then we can use this information to figure out whatever the problem is asking us to do. So the first one is how much of the NO2 would be produced. Well, we can take our 0.0154 moles of NO2 and convert that guy into a mass. That's going to be 14 plus 32, 46. 0.71 grams NO2. And now we can do the same thing here for the next part. It says, calculate the mass of the excess reagent or the excess reactant. And we know this is the excess. We have moles of excess. So all we have to do is convert this into a mass. 0.0066. 1 mole. And that's going to be our 30 grams. Going to give us a small number, 0.0066 times 30. 0.2, basically, around 0.2 grams. No. And that is in our excess. I would highly recommend using this method, and this is the way we're going to be teaching our general chemistry students from now on to do limiting reactant, because the ICE table sets things up really nicely. As long as you can figure out which X is going to be the one to limit it, you're good. And really, ladies and gentlemen, I went through the conceptual way to figure out which one is going to be the limiting, but it's always the smaller one. The smaller equals limiting. So whichever X is smaller is your limiting reactant, and that will always be true, always. All right, I need to wipe the screen again and scroll up. Number 24 is another limiting reactant problem. I'm not going to go over that one. It's the same as before. You know, since there is a coefficient in here, let me see if I can do this one quickly for you. All right. Since it's a little bit different. This is number 24. MnO2 There's my ICE table. Need moles. Always need moles with these, so we have the two reactants. The magnesium dioxide's already in moles. It's manganese, 0.086. And the hydrochloric acid, I'm just going to do that in the calculator, 48.2 divided by 36. So 1.34. Yes, I do see my mistake. I'm going back to fix it. .86. This goes down by x. This goes down by 4x. On the right-hand side, 0, 0, 0, plus x, plus x, plus x. And then we can solve for everything and do anything with that information at the end that the problem requires. Let's go through here. 0.86 minus x equals 0, and 1.34 minus 4x equals 0. X here is equal to 0.86. X here is going to be equal to 1.34 divided by 4, 0.335. We could go through the conceptual work here again to show you that this is true, but it is the smaller x that is going to be the limiting. So that tells me that the hydrochloric acid is a limiting. So let's go ahead and go back and plug that in here so that we can get our values here. It's pretty easy. And this one, 0.86 minus the x is going to be 0.525. This one, though, we're going to subtract 4x, and it should be 0, right, ladies and gentlemen, because that's our limiting. 0.335 times 4, and good, 0. Plug that in the calculator just to make sure we didn't make some kind of mistake down here with our calculations, but it turned out to be 0. So over here we have the exact same stuff. We're just adding, so we end up with 0.86 across the board. Oh, sorry, I was looking at the wrong one. .335. All right, and there we have it. Now the problem says how many grams of the chlorine would be produced. All we have to do is take the 0.335 of our chlorine and convert that guy into a mass. .3.8 grams of chlorine. Okay, so there's that one. Going on to the last couple here, we have 26 and 27 left. Oofta. All right. 26. Oh, 25 first. Differentiate between theoretical and actual yield. Theoretical is what we calculate. That's when we do stoichiometry problems. That is the 100%. That's the whole. That's what could be possible. Where the actual yield is going to be what happens when we do labs. A lot of times we don't get 100% success. So we lose some or get some impurities in it or something like that. So we can solve for that. And the way that we get the actual yield, the way that we get the percent yield is by taking the actual yield divided by the theoretical yield. So let's write that here. I know this is where we're going with question number 26. That's why I'm starting off this way. We're looking for percent yield. So we have percent yield, which is going to be, wow, that's really terrible. The actual divided by theoretical. And it's just the same thing as any kind of fraction. It's the part divided by the whole. Simple enough. So in this problem, we have a chemical reaction that occurs with freons causing a bad acid to be produced, and we're looking at a chemical reaction involved there. So if we have hydrogen fluoride right here being produced through this reaction, we want to figure out what the percent yield is of that hydrogen fluoride if 2.86 grams of it was produced, starting with 6 kilograms. So we're going to start with our 6 kilograms, figure out how much we should produce, and then compare it to how much was produced. So here is my initial stuff. We're going to go from there. It will stay in blue for a while. 6,000 grams. Notice I converted into grams because we have our grams of this from the periodic table. So calcium is 40.1, and we have fluorine, which is 19, 78.1. That's 1 mole. And we go through a mole ratio step. And then we can figure out our final mass of the hydrogen fluoride. 19 plus 1, that's 20 grams. Cancel, cancel. All these get canceled. We end up with Oh, I remember this. It's 3,077 grams of the hydrogen fluoride gas, which is equal to 3.077. I'm going to do 8 here. Around. Oops. 3.08 kilograms. We can go through the final process of percent yield, which is going to be our actual yield, which was obtained in the chemical reaction by doing this in lab. 2.86, 3.08. And don't forget to multiply this by 100 to get it back into percent. About 93% is our answer. All right, 27 is our last one. It's going to take up a lot of space, so let's wipe the board. Nitroglycerin, powerful stuff. It is a very common explosive, and it is very effective explosive. Its decomposition reaction is identified as this guy here. So here is our nitroglycerin. You should be able to figure that out based on clues. Talking about nitroglycerin, which is a chemical structure that we're not familiar with, and we say it goes through a decomposition reaction. Well, a decomposition reaction starts with one reactant and breaks into several other things. Besides that, we also know the other parts of the reaction. Nitrogen, carbon dioxide, water, oxygen. So that leaves this to be the nitroglycerin. This reaction generates a lot of different things. All of those products, plus lots of heat, and that sudden explosion happens, and we have that explosive device of dynamite, TNT, nitroglycerin, all the same thing. So if we do a chemical process related to this, we want to know how much oxygen can be produced. I don't know why. We're going to figure it out though. If we start with 200 grams of nitroglycerin, which is really kind of a lot. All right, so there's our 200 grams of nitroglycerin. Let's go back to black. Number 27. You know, the reason why I put the numbers up here is for those students that skip ahead of the video so they can keep track of what I'm working on. So you're welcome. 200 grams of nitroglycerin. So this is another time that I'm going to use a different abbreviation than the actual chemical formula. I'm going to say nitroglycerin and go through this process. So we have 1 mole of it. And we have some grams of it. That should be capital G. I'm not going to fix it. A lot. 12 times 3 plus 5 plus 14 times 3 plus 16 times 9. 227. Start canceling it as we go. All right, now we can go to the next step. We're looking for the oxygen. All right, so we have 4 moles of the nitroglycerin right here, 4, and 1 mole of O2. Cancel. 1 mole O2, 32 grams. O2, cancel. There we go. Let's figure this out. 200 divided by 227 divided by 4 times 32 gets us, not a lot, 7 grams. 7.04 grams of oxygen. Not a huge producer of oxygen. It's going to produce more carbon dioxide because look at that coefficient. Anyway, going on. Calculate the percent yield in this reaction if the mass of oxygen generated is only 6.5 grams, 6.55. Let's see. Make sure you can see that 6.55 grams. So we take our 6.55, 7.04. Gets us probably a 90% yield. 6.55 divided by 7.04. Yeah, 93% yield. All right, based on your answer above, what was the mass of oxygen that is formed? There's several ways that we can do this. But I'm going to go ahead and start over with the 200 grams of the nitroglycerin and just change the end part to nitrogen with one little change at the end. And I'll show you what that is when we get there. So 200 grams nitroglycerin, 1 mole of it, 227, 1 mole, and 2 is what we're looking for, and 4 moles of the nitroglycerin. And I bet that coefficient is wrong. So let's go back and fix that. Make that capital 2 while I'm at it. It is 6 moles of N2. 1 mole N2 is not 6. 32. Nope. Try one more time. I'm tired, guys. I'm getting through this. 28 grams of N2. Cancel, 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 cancel. All that cancels. So 200, again, divided by 227 times 6 divided by 4 times 28 gets us 37. Now, ladies and gentlemen, this is a theoretical yield. This is the answer if we had 100% yield, which we do not. And so we need to go through and identify with the 93% yield on this guy. So 37 grams of the N2 times 0.93 gets us our answer. 37 times 0.93, 34.4. Now we're making the assumption here that we're going to have the same percent yield for each thing, which is a reasonable assumption. All right, so there's chapter 3. Hope you enjoyed it.